Hello, everyone. So in this video, I want to talk about how we can look at the original problems we had a couple of videos ago, which were street routing problems. Now we can model these problems and come up with some solutions. So we'll model these problems using graphs and be able to express their solutions in terms of some of the vocabulary that we established last video. So let me recall the first problem, which was the security guard problem. And what was the idea? We have some map, and this map's a little different than the one that I had in that first video. It's a little simpler. But the idea was, maybe a security guard was at some corner, and they needed to walk a route through the entire city and check um, uh, to see everything is safe. But they didn't want to do things where they would repeat because they wanted to cover as much ground as possible within any given amount of time. So they didn't want to retrace their steps. And so the idea of a graph model presents itself here by basically taking each block in your street and drawing an edge. And then at each street corner, well, at least in some cases, to draw a vertex. And so what will that do? Well, what it'll do, and we'll pull this out here, is it will take this map, which has all of this decoration in it, and it will sort of strip it um, of all of these decorations, and we'll just produce some kind of a graph. So let's see if I can bring it down over here. And once we do that, we can uh, forget about the map itself and oops, and bring back the graph. And so now, what is our problem? Oops. Well, aside from being able to, okay, I left a block back here. Let me bring it up. Okay. Um, so what is our problem now? It's the same problem we had before. We have a starting point, let's say this corner here, and our security guard wants to walk the city streets in such a way that, you know, he's hitting every block once, or minimizing the amount of times he retraces his steps. And what you can do when we have a situation like this is you can simplify the graph. So we can really look at which corners are corners, so and label them as vertices. So I'll label this A, B, C, and here it looks like it's a corner, but in some, and maybe it is a corner, but it's not one where there's more than one intersection, so I'm not going to label that as a vertex. In other words, there's two roads coming together at once, and unless the security guard's starting there, I don't really want to label that as a corner. Similarly, this guy here, I'll just think of this as a single edge because the security guard's not going to turn on that point. But I'll label this E. Uh, let's say F, G, H, and I. And I want to say that everything else is sort of determined here. Um, and what we can do is, oh, I'm sorry. I do want to label this because maybe there's something that needs to be walked there. But then we have a couple of edges that maybe we didn't see before. So now we can label the edges AI, and then this whole route here is another copy of AI. So this is a multiple edge AI. Because again, I'm not labeling, even though these are corners, maybe in the street, the security guard is going to be walking that. He's not going to turn and jump into a coffee shop or anything. So you can kind of minimize the labeling a little bit and simplify your graph. And now, what are you asking if you want the security guard not to ever retrace any steps? Well, that depends on whether the security guard is going to start somewhere and end up back at the original place, um, or if the security guard is going to start in one place and end up somewhere else. So, so for starting and ending, at the same place, then the solution, this is part of the solution, if we were doing this, then the solution, then we want, ideally, an Euler circuit of this graph. Because what we're looking for is some path where we don't retrace any edges, so it's a path, and where we hit every single block. We hit every single block exactly once, and we end up back where we start. But that's exactly what an Euler circuit is. On the other hand, if we're starting at one point, one corner, and ending in another, maybe different, then the solution, then we want an Euler path. Now, this is what we want, and oftentimes we can't get what we want. That doesn't mean that the problem is over. That just means that the ideal solution is not attained or attainable, and we have to look for some other things to minimize or optimize our routes. Okay, so but in the ideal situation, this is what we would look for. If you recall, there's another problem, this mail carrier problem, and again, I've used the same new map and kind of drawn out. Now, what was the difference of the mail carrier problem? Well, I think the way I described it wasn't exactly perfect. The mail carrier, let's say, is actually walking, not driving, and that way they can walk along the side of the street one way or the other, or they can walk in the same direction. So what that means is that the mail carrier is sort of when he's walking down a block or she's walking down a block, needs to walk on one side and has to walk on the other side as well. They're not going back and forth across the street. But the direction doesn't matter so much. So in this problem, what happens is we don't want the mail carrier to just traverse once because they're not going back and forth. We want them to traverse twice. And so what we do in this case is we just put forward a multiple edge whenever there's two sides of the street that the mail carrier needs to deliver. And so I tried to kind of draw that type of a picture here, and we get a new graph. And again, we see, I won't label all of the vertices, but what we see is there's this edge, which is a single edge. And so really you could think of this as just a multiple edge and get rid of that. This edge is sort of a tortured edge, but in fact, it's just a single edge. So the visual representation or the illustration of the graph is not always exactly what we need when we're talking about a graph and a problem like this. It's really what we are looking for if we're looking for an optimal route is just sort of a path, a sequence of edges. And so we have all of these multiple edges. We're looking for, again, an Euler circuit. And the only difference between this and the previous example is now we sort of doubled up on some of these edges, the ones that had houses on both sides of the street. And so here again, we're looking for Euler circuits or Euler paths. Solve this problem. Again, it's not always possible, as we'll see in the upcoming videos, to find such Euler circuits or Euler paths. That doesn't mean the story is over or that you can't optimize. It just means that the optimal solution is not an ideal solution. You have to retrace some paths, some roads. Great. Now let's look at these bridges problems. These bridges problems are kind of interesting. And again, this is where a lot of graph theory stemmed from, is this original problem, the bridges of Königsberg. And what we want to do here is we want to kind of, again, strip away some of the noise from this problem. And so how do we strip away the noise? Well, what we're interested in, let's recall what the problem is. What we're interested in is we're interested in starting in some landmass. So maybe over here, for example, and we want to take a bunch of tourists on a tour guide of each of the bridges. And we want to do it in such a way that we don't have to revisit bridges. So we'd like to cross bridges, but without crossing again. So I can maybe try to do something like this, but now once I get to here, oh, I have to recross this bridge, and so that's no good. So that's one example. But the idea is, can we find one? Can we find a route where we start on one landmass and we move to the others across bridges in such a way that we never cross the bridge twice? And so if we're going to come up with such a model of such a situation, we have to, and if it's a graphical model, we need to talk about vertices and edges. And so what the idea here is we turn each landmass into a vertex. So we'll take, here I'll use some colors so that we don't, so we can see them. So we'll take each landmass, A, B, C, and unfortunately the island is very dark, so but I'll write D there. Hopefully people can see that. And now we're going to connect land masses if there is a bridge. So for each bridge, we'll draw an edge. In fact, they're already drawn in pink. We've got this pink, but we're going to kind of connect them up. This pink, so this pink is connecting to B, this pink is connecting to B, connecting to B. All of these connect to D because they're in this landmass. This pink is connecting to A, this pink is connecting to A. So in other words, if it's connecting to a landmass, I'm going to connect it to the vertices. All right, so now let's see. Let's pull away the noise and see if we can't see what we've got here. All right. So we've got this picture. It's a little messy, but now that we have it, let me see if we can clean it up a little bit. So I'm just erasing the bridges now and drawing edges. So there were two here. So I'll just draw two. And B is too far away, so let's bring B a little closer. And this is pretty horrible. So let's erase it and then we'll redraw it. And again, A is pretty far away. So let me just erase this, move A a little closer. And I had erased two from D to A, so let me redraw those. And again, let me redraw, get rid of that and redraw one more here. All right, now all of a sudden, I have something sort of unrecognizable. I have 4 vertices and 7 edges, and I've got a graph. And this is maybe the Königsberg graph. And what we're asking again here is we're asking to start at a landmass and find an Euler path. So our solution, if we can find it, will be to find an Euler path. If possible. And you may see a bit of a trend here that in each of these problems, we're looking to find an Euler path. Again, in this problem or in other problems, it may not be possible. But if it's not possible, then you see if you can minimize how many times you're crossing a bridge. And that's more this bridges of Madison County problem, is that we've got several bridges, but remember in this problem, it just costs some money to cross a bridge. So what you want to do is you want to take a picture, you're a photographer, you're trying to take a picture of every bridge. you'd like to minimize spending extra money if you have to cross a bridge twice. You'd like to minimize the number of times you cross any bridge, or all of the bridges, let's say. So, and in this case, you can kind of readily see, because it's almost already labeled, the vertices. And here we could just go ahead and label them on the side. We could say, okay, well, we have A, B, C, and D. These are our vertices. And we have two more. I didn't label L and R. And then we have a bunch of bridges, and the bridges are sort of labeled. We can go from L to R to L along the Washington Bridge, the Truman Bridge from R to A, the Lincoln. We've got two bridges from R to B, the Lincoln and the Hoover Bridge, so we'll draw multiple edge. We've got another bridge from R to L over on the east side of town. We've got a bridge from B to D, the Kennedy Bridge, the Adams Bridge from D to L, the Monroe Bridge from C to D, the Roosevelt Bridge and Grant Bridge from C to L. So we've got two edges there, and a Wilson Bridge from A to C. And we get this graph. Again, it's doesn't look exactly like the picture, because we've sort of collapsed all of the landmass up in the north and all of the landmass in the south to a single vertex. But the problem that we're asking about finding an Euler path, or minimizing the number of repeated edges along a path, well, I guess not along a path, but along a route, is still a valid question, and it can be just asked knowing what the graph looks like. So let me fix this R as, let's write R. So find a route which minimizes repeating edges. And of course, the ideal situation is to find an Euler path. All right. So this is a way, what we're seeing here is that there's a way to take these concrete real world problems and use some graph theory or some graphs to recast them into some simple mathematical structure, whose ideal solution is a well-defined term, an Euler path or an Euler circuit.